right, so hi everyone. Thanks for coming for this keynote from Numalis, from the AI in the fog of war. So today I would like to share with you some thought we have regarding the use of AI in the battlefield, and especially on the way of balancing automation that we all want of systems, but with trust. Because that's the main issue of adopting AI today, is how are we going to trust an automated system based on AI? So, please remember that from even centuries ago, Clausewitz was giving us a good advice and say that war is more than a true chameleon. And what he meant by that is that in war, system does not adapt. They change all the time. And this is the reality in the 17th century, and today it's still true. And so in the battlefield, things change. And we need to take that into account when we're going to define systems that have to handle this change. And so first, when I'm looking at the battlefield right now, there are several characteristics that are striking to me as an industry. Is first, dispersion. Today, you cannot, group a large portion of your forces in one place in order to have an effect, because you're going to get destroyed way before you're able to move. So you have to disperse a lot of your troops. And so all the effectors are far away, and they have to coordinate one another in a way that is sufficiently efficient in order for them to cooperate. And that's the second aspect, that you have to disperse, but then you have to coordinate. And that's painful because you're coordinating both the Navy, the Air Forces, the Land Forces, Special Ops, information. You have to coordinate all of these in order to maybe have an effector from the Navy helping an effector from the aerospace, helping the infantry to have an artillery strike working. And that's a lot of information, that's a lot of pain to process in a time and efficient manner. But it's necessary, otherwise, since you're not grouping your troops, you're stuck with having coordination. Then you have to have speed. If you're too slow, you get discovered, the enemy has moved, he has changed, he has adapted, and so your whole process and chain of command is not relevant anymore. And so your carefully planned effectors, they're not working. Your dispersion plus coordination is not enough in order to have the right effect. So here we can see that now AI system and digital system might be quite helpful, because you can shorten, the time span you're going to spend on processing information and maybe coordination. And so if you don't have speed, you might lose your effect and your momentum on the battlefield. So we know dispersion, coordination, and speed. But we still have the need of, what? Okay, it doesn't work at all. Okay, will you help? All right, so it's moving up there, but not here. Je vois. Ça, quand j'appuie là, ça marche. Thanks for the heads up. All right. Thanks. All right. Dispersion, coordination, speed, mass. Right, so we have to have mass still, because one effector can get destroyed and you cannot just put all your eggs in one basket. But mass is not just, grouping all your forces, like we said. You need to have another form of massification. So right now, one solution is to say, well, I'm not putting my soldiers on the front line, I'm going to put a piloted system on the front line that will be operated by one soldier. So fine, you have more effectors, but you're selecting a portion of your forces in order to operate them. So it helps, but it doesn't create more mass. In order to create more mass, you need to have new layers in order to command a fleet, not just one operator for one device. If one operator can suddenly have many devices, then you can create mass, given you have the industry production that following in the background. So here again, you see that digitalization and automation will be crucial in order to not just pilot a device, but to operate a fleet of devices. So I know that all of my systems are going to get connected one another. There will be coordination between all of them. I might also manipulate fleets of systems by just one operator. So where am I going to put some AI system within it? Where is the key strategic place I should put an AI system within that? So there are plenty of ways to create effectors by combining different devices. So if you remember World War I, for example, the combination of infantry and artillery was one way to create new effects on the battlefield. On World War II, it was the combination of planes plus tanks that was creating a lot of effects. So even recently, we can see that, for example, in the Ukraine war, we have new effectors that take place by combining soldiers plus drone plus artillery to destroy, for example, armored vehicle in a very timely fashion and very fast fashion. So it's all about combination. So what kind of effectors can I improve with an AI system and combine with another in order to produce an effect on the battlefield I want? So what are the right combination? So it might be like a lottery because we need to experiment a lot about the different effectors we have, and we have plenty. We can just look around and see that different effectors, different effects, different way to operate them, different way to connect them. And so we have tons and tons of combination to try it out. And mostly on the battlefield, everyone will try them out entirely in order to find the right ones. So for example, you might want to put some AI system by combining, some tanks, drones, and micro drones. Or you might want to use command center plus drone plus anti-tank. I don't know. There is all of your creativity here you can express if you want. But you don't. You have to remember that it's quite important to also put a doctrine onto that. It's not just about combining stuff and hoping for the best. There is also the way you're going to use that and what kind of doctrine of use you're going to implement in order to make that work. So right now, if we look at the newest doctrine, you have like the multi-domain operation, you have the mosaic warfare. So you have plenty of new concepts that you can use in order to foster your combination into a new effect using AI. But once you define the right doctrine, the right effectors, and the right AI system, then you have to go to your engineers and your operators, and they have to trust the system. And that's painful also, because right now, most of the operators don't trust like a black box with a stamp AI on it and say, yeah, trust us, it works. This is a tank, yeah, that's it. You have to have a better understanding on what's happening inside it. And so you have to lift a little bit, the veil on the corner and look inside to see whether or not it's a right way to say this is a tank, and if you can trust it will be a tank. And so when you want to do that, here you can take example from the civilian domain. So for example, in the aeronautic, we're launching more and more AI system in avionics system, and we want to build a way to make trustworthy AI. And so, for example, here you have different way to define what is the domain of operation of an AI system that has to land on the runway. And so this is an example from the EASA. And so you have the mathematical model in the center. So it's a pure mathematical way to say, this is my reality. It's a runway, it has a geometry, I know exactly what it looks like. Then you have the real world on the left, where you know that this is a real picture of a real runway, and I can try to land on this one. And then there are the corner cases, the stuff that shouldn't happen but might happen. And so maybe your runway is damaged, maybe you have like an explosion on it. And so you have to have like fail-safe in order to handle these weird cases that can occur. But it's all in a domain that is understandable by a human and that a certification authority can handle. They understand what you want to build, and they agree with you that, yes, this is the real world we're expecting. It's a presupposed operational design domain, ODD. But remember, in war, in the battlefield, things change. And so, what happens if suddenly my tank doesn't look at all like a tank, and it looks like Hello Kitty with a cannon on top? So obviously this is a stupid example, but the reality is that the enemy will adapt in order to get out of the ODD that you have in mind. It will be its sole purpose to fail your system by changing the ODD, changing the parameters, so that your system that would say that this is a tank would not say that this is a tank. And then suddenly it's like you're invisible to its system. So this is the challenge. We need to have like a trustworthy way to build an AI system, but we have to face the elephant in the room is that the ODD we're going to build the system on will not be the same in real world. So how are we going to build system? So the classical way is that you're starting with, a specification sheet that you're discussing with your MOD, and you spend years, ironing out the details on that. Then you go to, design, and you build a perfect system in a mathematical way. Then you test it, and if it's convincing enough for your MOD, you go mass production. You put that on planes. You deliver that on a forward operating base, and then your soldier can have it. And so, obviously, this takes time. And in front of the soldier, the battlefield is changing all the time. And so my tank is suddenly a Hello Kitty tank. And so the feedback that my soldier will have to make will probably go to the specification guys that are probably thousands of miles away from the battlefield. And they will have to redo the cycle in order to adapt the system against the new pink tank. So this is not ideal. Especially if the speed of war is accelerating, like I said. So we need to find a way to just have to make one step back, for example, in the forward operating base, and adapt the system there, and not have to go through the whole chain. So this is where it's new. This is where the industry and even the MODs have to work together in order to define new ways to allow that in a safe way in order for the soldier to adapt on the battlefield. And it will be all about the domain of operation. So what is the domain I want to cover? So initially, I've got this nice domain where I know what are the edge points, the corner cases, and what are the cases I want to verify. And so this domain, it's pure, it's well-defined, and I can verify as much as I want when I'm at home in peace, when I'm building the system. But the real domain will be outside of this nice bubble. And even in this nice bubble, how am I going to test it? So usually what we do when we're doing AI as data scientists, that you take some sample inside the domain and you test on it. And if you have sufficiently, success on that, you're happy. And you say, yeah, 99% okay, so it should be okay. But there are plenty of other examples you're not covering that are different from the one you're covered. And so on these one, you don't know exactly how your system is going to be efficient or not. So there is still one, basic assumption that we need to cover the space we want to verify on, and have something that is convincing enough in order to put the system on the market and on the battlefield. So one might think that, okay, I'm going to generate lots and lots of data and I'm going to cover it all. Well, that might not work. There is plenty of possibilities and almost an infinite number. And so evidently you cannot just, brute force your way out of it and just, put more data in it and say, yes, I've tested it all, it will work. This is impossible. So we need another way in order to cover more space in the domain we want to verify and make sure that the system works. So this is where new technology, such as the one we developed at Numalis, is coming through. Is that from one data point, we can explore around it. And so in this mapping of around the data points, we can verify whether the system is working or not. And so here we're not just testing, we're trying to prove. We want to prove that the system is working as intended on part of the domain. And so the more you're covering, the more you're going to trust your system. And this kind of methodology is not just for military. So this is basically what is also recommended from the civilian domain. Here I'm putting the AI trustworthiness from the EU AI Act, so the regulation on AI. And so there are several pillars they want industry to tackle, and one of them is technical robustness and safety, and basically describe this kind of methodology I just described you. So you have to verify your system on your intended domain of operation, and you have to make sure that it works. So this is not entirely new. This is grounded also for the civilian domain. So what does it mean, for example, to be robust? So remember, you have this space where you can build around the data point, and around this data point there are millions of variations of the existing data points. So for example, this tank, it can have like different defects, it can have different sensors that is taken. So you have many edge images around this. And you want to consider all of these images like a whole and say, okay, would these images set will be considered as, tanks all the time? Can I prove that? And so you have technologies now, you can propagate, this kind of mathematical space and see how, the AI system is processing it. And you can verify at the end whether or not it's always contained within the tank box, or even go outside and say, no, it might not be always tanks. Sometimes it will be something else. And if it's red, well, the system is not stable. If it's green, yes, it's stable. So here you have like a clear metric, a clear process, to verify whether or not your system can handle perturbation that can come from the domain of operation. And this is the kind of stuff we can do with our tool, exactly. So, another aspect on robustness is that usually when your system is confronted to stuff that it knows, it's quite stable. Like it can handle a lot of perturbation of stuff that it knows. But when it sees something completely new, then usually it's not quite stable. Like it doesn't process it with the same amount of robustness. And so by comparing how much your system can handle, you can discover whether or not you're facing something completely new automatically. And so even if the operator is not here to say, hey, this is a weird tank, your system might be able to say, I'm seeing something, I'm not sure I know. I might use an operator here to have some help. And so here you can see that you can have still human over the loop to monitor when the system is kind of failing and kind of warn you that you might not be using me too long because right now I'm seeing stuff I don't know and I might took the wrong decision. And so help me. So these kind of ideas, this is what we're currently being putting in standards in the civilian domain in order to help the industry structure themselves in order to define what is the right robustness for the system and have the right process to verify it. And for example, at the very end of the process, they end up with stuff like that, where it's kind of a robustness map, where they can project the domain on their currently operating, and see whether or not there are spaces where, well, here my system is not very robust. It doesn't really understand what it sees. Here it's better robust. And so you can then use this information in order to improve, in order to put safeguards on your system, and you can document your system for the ultimate buyer to see how much you can guarantee. So these kind of ideas and results. They're existing now, and you can use them in order to describe the system better and trying to better convince your user on that. So that's robustness. Another aspect that is currently being explored is also the explainability. Because if I'm not understanding why my system is acting, I might not trust it. And so here we are facing quite a nightmare when we are dealing with neural networks and deep learning. So this is an example from a project from Google called Inceptionism, where they're trying to extract what a neural network is seeing on a picture. And so the picture, if you squint your eyes a little bit, you're going to see that it's a truck in a field with a tree behind. But for the AI system, no, it's not that at all. Because the AI system is trying to see dogs and cats and birds. And so it tries to see dogs, cats and birds everywhere. And so it's like it's hallucinating or dreaming that it sees stuff that doesn't exist. And so if I'm trying to explain what the system is doing, I might be facing this kind of disconnect between what the system does and what I think it should do. But there are still stuff we can do. So for example, if I'm using the tank example again, imagine you have like two neural networks that you've trained, like two AI systems, and they're both fine. They say that, yes, this is a tank, and I'm sure of it. And you say, yes, this is a tank, so I'm happy with the two of it. But we're using techniques of explainability. You can extract why the system is taking its decision. And so, for example, on the top right, you can see that the system is using part of the images that are not tank, it's just ground. And so you say, well, why is that? And the truth is on this system, the system is biased. There is a watermarking in some of the training pictures on the bottom left, on bottom right, and the system has just learned to read the watermarking on the picture. So it's a silly example again, but it shows you that you can compare two systems that seems fine and have a better interpretation about which one is best for the right reasons. So the bottom one is using only pixels on the tank. The upper one is not. So I might not want to use that. So this is an example on how we can build processes to build trust through explainability of AI system. And all of these are developed in a tool called Sample that we can showcase in our stand on Numalis. It's on around the GCAT. And it's a tool that is meant to help AI engineers to verify that their system is robust and explainable. So it has like a nice graphical interface, but also an API because it has to be easy to use. And we can deploy that, for every company, or they're on-premise or on SaaS, for one set of users or for a scaling number of servers. So we can adapt to almost everything, every cases you have. The point is that we want to integrate into your tool chain because you already have a tool chain to build AI. So no need to replace it. We just want to, be another tool in the toolbox that you're using. And this tool chain, well, it has to correspond to a new way of validating and building AI system. So what we advocate is that it's not only enough to specify, model your system, train your system, analyze your system, integrate your system, and deploy it. You have also to adapt it. So you have this back loop that is new, that you have to put into your life cycle of your AI system, which is not the case today. Today we just have a straight arrow toward the deployment phase. And this back arrow, it has to allow to do all the training and to analyze integration and deployment really fast because you don't want to go to the specification board, you just want to adapt the system. And this is new. This is where there is still work to do and standards to be written and industry to cooperate together in order to build from the guy who built the frameworks to build AI to the guy who integrates AI into a weapon system or a command center to coordinate themselves together and with the MOD to build a chain that everyone can trust. One final challenge we have to tackle is also the footprint of all of that, because training models is not cheap. Usually it takes like huge amounts of GPUs and RAM and etc. And so if I want to do that in a frugal way, if I'm using this term, I need also to find a way to either miniaturize it or find another way to build it. Because I'm not going to put on the backpack of a soldier racks of GPUs. He doesn't have time nor space to do that. Ultimately, what we want to build is a way to have like something like that, like an AI info, AI in a forward operating base, like a shelter that you can, drop, put on a forward operating base. That's when the soldiers come back, they can dump all the data they have, all the problem they have, and one shelter allows to do the whole process of adapting there and then redeploy it without having to ask anyone else in the homeland. This would be the concept for us at Numalis that would help to adapt more quickly on the battlefield. It's definitely not what we have today, and it's definitely something that we need to discuss with the MODs, because that's changing a lot. And also the industry will not maybe like it, because, well, they won't have the control of all the new version that's going to pop up, because that will be on the forward operating base. But I guess that from my perspective, this is the way forward in order to make sure that we keep the advance we have and we stay ahead of the adaptation of the enemy. And as a way to conclude that, like I said, there is a lot of standards missing. And so what I'm hoping is that we're building standards in ISO and Sensenelec for the civilian. But I'm hoping that maybe here in this community, we can find also other person to help us build some standards in order to standardize how we're going to build AI system in a responsible way, in a trustworthy way, all across the allies. And so here, there is still a lot to do. The only document I've been found on the certification of AI from the NATO is still, in flux. There is a lot to be specified, a lot to be really described precisely what we want and how we're going to do it. And I guess for that we need all of you to help this community to build all of these. And I think that's my final word, and we still have time for questions. So I guess there is a mic coming up if anyone has one. And thanks a lot for your attention. Any questions? All right. All digestion is... No questions? One time, two time? Advocate? All right. Thanks a lot for your attention. We can see us at Numalis around the GCAT in City 74. Thanks a lot.